Hi everyone, this is Professor Oaks, and in this video we are going to talk about the differentiation and integration of power series. So here is the function that is given by a power series and has a radius of convergence of r greater than 0. So if this has a radius of convergence greater than 0, then on the interval from a minus r to a plus r, f is continuous, differentiable, and integrable. But please note that the radius of convergence obtained by differentiating or integrating a power series is the same as the original series. However, the interval of convergence may differ as a result of the behavior at the endpoints. All right, so here is, I guess, what you need to know as we go ahead and start this. So for the absolute value of x minus a is less than r, then if I want to differentiate this power series here, then f prime of x is dx, so the derivative with respect to x of this series. So sum k equals 0 to infinity of ck x minus a to the k. Now remember that ck is a constant, but remember also, though I'm taking the derivative with respect to x, so there's the variable. So ck is a constant. So then this is going to be sum k equals 0 to infinity. Now I can actually interchange these or bring the derivative inside and just take the derivative of the terms, all right? So the derivative with respect to x of ck x minus a to the k, and then because the ck is a constant, I can actually bring that out in front of the derivative. All right, so ck, and then I need the derivative with respect to x of x minus a to the k. So I'm going to use the power rule. So if I use the power rule, then I have k times x minus a to the k minus 1, and then I need the derivative of the x minus a. So don't forget to use the chain rule, and the derivative of x minus a is 1. So then if I simplify all of this, I have sum k equals 0 to infinity. Well, actually, by the way, believe it or not, the one thing that I did actually, I kind of did not say this, but this actually, now that I wrote that, I realized it did not make sense. This actually is a 1, and this is a 1. Because look at what is actually going on here. Here's why this can actually start at 1, all right? Because look at this. This first term was a constant, right? So when you take the derivative of it, the dx with respect to, with dx with the derivative with respect to x is c0 will be 0. So I can actually start at the first term here. All right. So try to remember that as well. All right. So then this is ck times k x minus a to the k minus 1. And then if I write out the terms, you'll see it's exactly as I said. It's c1 and then times 1 times x minus a to the 1 minus 1 plus 2c2 x minus a to the 2 minus 1, and then plus 3c3 x minus a to the 3 minus 1, and so on. So I have c1 plus 2c2 x minus a plus 3c3 x minus a to the second plus 4c4 x minus a to the third, and so on. All right, so now let's go ahead and look at the derivatives of these power series now. So now for the derivatives. So if I want I said the derivative. So now the integrals. All right, the integrals. The integral of f of x dx. So that will be the integral of the sum k equals 0 to infinity of ck, then x minus a to the k, and then dx. And then I can interchange the integral and the sum here. So I have sum k equals 0 to infinity of the integral of ck x minus a to the k dx. And then the ck is a constant, so I can bring it out in front. So sum k equals 0 to infinity of ck. Then I just apply the power rule here, the power rule for integrals. So it's times x minus a to the k plus 1 all over k plus 1 plus some constant c. All right, so if I write out the terms, I have c0 and then x minus a plus c1 x minus a squared over 2 plus c2 x minus a cubed over 3 and so on, and then plus c at the end. What a time to be alive. All right, so now hopefully you see that all I really did was take the derivatives and the integrals of each of the individual terms of the power series here. So let's try another example here. So I actually don't know where the next page went to, so that's really not good, but let me see if we can go ahead and find that here, or else I'll just sort of try to figure out how we can write that on a piece of paper, because for some reason that is one page that is missing, because it should be page 235 here. So since I don't have that page, I am just going to go ahead and write it on a separate sheet of paper. So let me find that piece of paper for all of you. All right. And I don't know what sort of rodent here may have eaten it, but that's okay. I'll figure it out, and I will actually, you know what? Here, I found it right now. So there we go. After all of that work, I found page 235, the missing page that I have here. So we're given a series, and we want to find the derivative, the integral, and the radius of convergence of the resulting power series. All right, so here we go. Let's go ahead and figure this out here. So let's look at the derivative. So f prime of x is going to be dx of the series. So that sum k equals 1 to infinity of negative 1 to the k plus 1 times x to the 2k minus 1 over 2k minus 1 factorial. And then I'm going to interchange the sum and the derivative. So the sum k equals 1 to infinity of the derivative with respect to x of negative 1 to the k plus 1 over 2k minus 1 factorial times x to 2k minus 1. And I'm rewriting this so that I can see the ck here, and I can see the x minus a to the 2k minus 1 here. All right, just so that you're clear on sort of what is going on here. All right, so now I am going to rewrite this. All right, so that it's sum k equals 1 to infinity, and then I bring out the constant. So I have negative 1 to the k plus 1 over 2k minus 1 factorial. And then I go ahead and I use the power rule here. So 2k minus 1 times x to 2k minus 1 power. And so then I can simplify this here. So it's sum k equals 1 to infinity of negative 1 to the k plus 1. And then 2k minus 1 factorial is really just 2k minus 1 times 2k minus 2 factorial, and then times 2k minus 1, and then x to the 2k minus 2 power, and then go ahead and divide out the 2k minus 1. So I'm left with the sum k equals 1 to infinity of the negative 1 to the k plus 1 all over 2k minus 2 factorial x to 2k minus 2. So then this is going to be the CK, and this will be the, yep, so that's going to be the CK, and this is x minus a to the 2k minus 2. All right, now let's find the integral of this power series here. So the integral of f of x dx will be the integral of the series. So sum k equals 1 to infinity, negative 1 to the k plus 1 times x to 2k minus 1 all over 2k minus 1 factorial. So I'm going to interchange the integral and the sum. So I have sum k equals 1 to infinity of, well, what would that be? Integral of negative 1 to the k plus 1 all over 2k minus 1 factorial times x to the, oh, and I did not write dx over here. So x to 2k minus 1 dx. And then I see that this here is a constant, so it can be brought out in front. So I'll just use the power rule for the integral. So I have negative 1 to the k plus 1 over 2k minus 1 factorial. Then the power rule for integral, so x to the 2k minus 1 plus 1 over 2k minus 1 plus 1 plus c. And then I will go ahead and I will simplify this here. So it's sum k equals 1 to infinity, and that will be negative 1 to the k plus 1 all over 2k minus 1 factorial times 2k, and that's x to the 2k plus c, and then 2k times 2k minus 1 factorial, it's just 2k factorial. So this will be equal sum k equals 1 to infinity of negative 1 to the k plus 1 over 2k factorial times x to 2k plus c. So then here would be the ck for the integral, and here would be the x minus a to the 2k power. All right, so now they want us to find the radius of convergence. So remember, this will not be too difficult to find here. So all we really need to do now, by the way, I will say that in order to find the radius of convergence, remember that generally, right, you would want to make sure that this was in correct power series form, right? So the series was going to be sum k equals 1 to infinity, negative 1 to the k plus 1, x to the 2k minus 1 over 2k minus 1 factorial. But if you let w be 2k minus 1, then you have that if k was 1, then w was actually 0. So if it's the sum, k equals So W, okay, so W equals 0 to infinity of -1 to the, now if W is 2k minus 1, then W plus 1 is 2k, and then that means that k is equal to W plus 1 over 2. So we have W plus 1 over 2, and then x to the W over W factorial. All right, so even then, this is a little bit easier to deal with because now my Cn plus 1 will just be -1 to the n plus 1 over 2 over n plus 1 factorial, and Cn will be -1 to the n plus 1 over 2 over n factorial. And then since I just need the absolute value, I need limit as n goes to infinity of the absolute value of Cn plus 1 over Cn. So that's limit as n goes to infinity of, well, that's actually, what does that give me? That's going to be, 1 over n plus 1 times n factorial over 1, right? And so then I can divide out the n factorials. So, well, actually, wait a second. That's not quite right. That's actually, what is this going to be? This is going to be, yeah. So then I'm going to have limit as n goes to infinity of 1 over n plus 1, which will be 0. All right. So just try to remember this, that this is not going to be as difficult as it might actually seem like it is. All right. And so then, well, there we go. We know that since the L is equal to 0, that means that the radius of convergence is going to be infinity. What a time to be alive. And so the other thing to note is that these other two series, a series for the derivative and the integral, also have the same radius of convergence as the original series, which is in this case infinity. All right, so let's try to look here at some known power series here. So there are two famous power series. Try to remember these and memorize them for the rest of your life. So one of them is 1 over 1 minus x, and that will be 1 plus x squared plus x to the third plus x to the fourth, and so on. So that's sum k equals 0 to infinity of x to the k power. And this actually converges for -1 less than x less than 1. In other words, for the absolute value of x less than 1. And then the second one is tangent inverse of x, that's x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and then plus and so on. So it's the sum k equals 0 to infinity of -1 to the k, and then x to the 2k plus 1 all over 2k plus 1, and this converges for the absolute value of x less than 1, and this series is called Gregory's, all right, Gregory's series. What a time to be alive. All right, so I hope that you really enjoyed that. So just again, remember both of those series for the rest of your life. Just memorize both of them, and we won't have any problems here. So now let's try another one here. So starting with a known power series, obtain a power series representation, and find the radius of convergence of the resulting power series. So if I just look at the t over 1 minus t squared, I see that it sort of looks like this first series here, but I could factor out the t, so make it t times 1 over 1 minus t squared. And then if I let x be t squared, then I have, all right, like I can just do that. So wherever there is an x, I'm going to put a t squared. So it's t times the sum, k equals 0 to infinity. Now remember, wherever there was an x, I'm going to put a t squared. So t squared to the k power. And then I'm going to bring this t inside. So I have sum, k equals 0 to infinity, of t to the 2k plus 1. Now, here's what I'm going to do. I know that this is equal to this series, so I'm going to substitute this in. So I have the integral from 0 to x of the sum from k equals 0 to infinity of t to the 2k plus 1 dt, and then I am going to interchange the sum and the integral. So this will be the sum, k equals 0 to infinity, of the integral of 0 to x of t to the 2k plus 1 dt. Then I'll use the power rule here. So then I have sum, k equals 0 to infinity, of the integral from 0 to x. And actually, again, I'm going to integrate here. So let's just use the power rule here. So I have t to the 2k plus 1 over 2k plus 1, evaluate it from 0 to x. So if I do that, I have sum, k equals 0 to infinity, of t to the 2k plus 2 over 2k plus 2, evaluate it from 0 to x. So let's evaluate the integral now. So I have sum, k equals 0 to infinity of, all right, so what will this be here? This will be, well, if I look at this, this will be x to the 2k plus 2 over 2k plus 2 minus 0 to the 2k plus 2 over 2k plus 2. And then, well, that sum k equals 0 to infinity of x to the 2k plus 2 over 2k plus 2. And that is the integral here. So now all we need to do then is go ahead and find the radius of convergence of the resulting power series. So, well, this should be fairly easy to do because we know that the CK is actually 1 over 2K plus 2, and this is x minus 0 to the 2K plus 2. So just try to remember that we can use the W is equal to 2K plus 2 again. And so then we have a series that starting from, well, K is 0, W is 2, so 2 to infinity of x to the w over w. So then CW is just 1 over w, and CW plus 1 is 1 over w plus 1. So if we want this limit here, we have limit as n goes to infinity of the absolute value of Cn plus 1 over Cn. So it's a limit as n goes to infinity of 1 over w plus 1 all over 1 over w. And so that ends up being, just if you find that limit, it ends up being, well, 1. All right, so since the L was equal to 1, and I'll write that over here. So since the L is equal to 1, that means that the radius of convergence is 1 over L, so it's equal to 1. So R is equal to 1. All right, so there you go. So the original series that we started with would have also had the radius of 1, but what we were dealing with, remember, we were dealing with the something like if we had the integral in front of it anyway. So there we go. There is how we would do this one by starting with a known power series. So let's try another one. All right, so here we go. We have 1 plus x squared over 1 minus x squared squared. So remember that our known power series were 1 over 1 minus x. So that's the sum, k equals 0 to infinity, of x to the k. And tangent inverse of x was sum, k equals 0 to infinity, of negative 1 to the k times x to the 2k plus 1 over 2k plus 1. All right, so here we go. So what are some ways that we could actually go about doing this? Well, this one is actually a little bit harder than the last one, because what you need to actually remember is that if you look at the just something that looks similar to one of these two series. All right, that would be, well, x over 1 minus x. So if I look at this, the derivative with respect to x then of x over, say, 1 minus x squared then. All right, that's something that could be plausible. Then if I find the derivative here, then that will be, well, the 1 minus x squared times a 1 minus an x times a negative 2x all over the 1 minus x squared squared. So then if I simplify this, I have 1 minus x squared plus 2x squared. So that's 1 all over a 1 minus x squared squared. So that's 1 plus x squared all over 1 minus x squared squared. So that is the derivative with respect to x of x over 1 minus x squared. But guess what? That is actually equal to this, what we want to find a series for. So now, think about this then. All right, here's the good news, is that, well, x over 1 minus x squared, we already know that is equal to, all right, so remember in the last problem we had t over 1 minus t squared, but now we just have x over 1 minus x squared. But guess what? We did actually, right, remember, we did actually find the series for that. It's just, if you remember what happened, we actually found it right here. It's just that we had not actually integrated it yet. So this is actually the series. All right, so it's sum k equals 0 to infinity of x to the 2k plus 1. I'm not going to show that again. So then the derivative with respect to x of this x over 1 minus x squared is actually the derivative with respect to x of the series that we just had. So k equals 0 to infinity of x to the 2k plus 1. And then you can go ahead and use the power rule. So let's switch the order of the derivative and the sum here. So we have sum k equals 0 to infinity, derivative with respect to x of x to the 2k plus 1. So let's use the power rule here. So sum k equals 0 to infinity of 2k plus 1, x to the 2k plus 1 minus 1, and then it's just sum k equals 0 to infinity of 2k plus 1 times x to the 2k. What a time to be alive. Now, if I want to go ahead and find the radius of convergence, then the ck will be 2k plus 1. The x minus 0 is to the 2k power here. So what do I need to do here? Well, I just let the w be 2k, and then that means that, well, this is just the sum w equals, so if k is 0, w is 0, so w to infinity of, if w is 2k, this is w plus 1, and then x to the w, so cn is n plus 1, cn plus 1 is n plus 1 plus 1, which is n plus 2. So then all I need to do is find the limit as n goes to infinity of the, well, cn plus 1 over cn. So that's limit as n goes to infinity of n plus 2 over n plus 1. And I know that's equal to 1. And so since the L is equal to 1, that means the R is 1 over L, which is 1 over 1, so R is just 1. What a time to be alive. So hopefully you're enjoying this because we're not done yet. So here is the next one. So there's always time for more Power Series. All right, so it's not like Power Rangers who went away at some point because people got bored of watching them on TV. This is Power Series. So now, let's look at the next one here. Natural log of 1 plus x over 1 minus x. So this doesn't look like one of the series that we've had so far, but let's use the rules of logarithms to simplify this. So this will be natural log of 1 plus x minus natural log of 1 minus x. Then, guess what? I know this, all right? This is a known fact here. So what I'm writing down next is a known fact, so don't forget it. The natural log of x is equal to the integral from 1 to x of 1 over t dt. So this is a fact to memorize for the rest of your life. And if you have not memorized that, now would be a great time to memorize that. So let me show you this fact right here. So give me a second to locate it. So here I have the definition of the natural logarithm function. So here it is. The natural log of x is equal to the integral from 1 to x of 1 over t dt. So if you've never seen the definition of the natural logarithm function, there you go. So you need to memorize that. So if you have any calculus book that you would like, just take any of them, all right? Just memorize every page, and then you'll know every definition you'll ever need to know to do any form of calculus. So now, let's go ahead and look at how this might look like one of the series that we already know. Well, in all honesty, this doesn't even look like one of the series I already know. However, all right, the good news, if you think about this, all right, the good news is that I can rewrite this right here using the definition. So this will be the integral from, well, 0 to x of 1 over 1 plus t dt. So why is it 0 to x now? Well, you really just have to think of this as a u substitution here, right? So if this was your u, right? U is 1 plus x, then if x is actually going to be, where is it? Where is it at? Hold on. Let me find it for you. Yeah, so if that's u of 1, then 1 minus 1 is 0. So you have to start at 0 instead of 1 now. So now this will be minus, all right, and here's the minus, the integral from, try not to mess this up, all right, and actually think about this though. It is one of those things that you do not want to mess up, so do not mess this up, please. It will be similarly, all right, 0 to x of negative 1 over 1 minus t dt. So try to remember this for the rest of your life. Now, how are you going to know to put the negative 1 there, like, as a reminder, all right? Well, remember, the derivative with respect to x of 1 minus x is 1 over 1 minus x times the derivative of 1 minus x, which is negative 1. So it should be negative 1 over 1 minus t. So please keep this in mind for the rest of your life. All right, now we want to go ahead and try to write this in the known power series form. So remember, this is what we know. We know that 1 over 1 minus x, this is sum, k equals 0 to infinity of x to the k power. So what I'm going to do is I'm going to rewrite this. So it's integral 0 to x of 1 over 1 minus negative t dt plus integral 0 to x of negative 1 over 1 minus t dt. And actually, well, if I make that plus, I actually do not need the negative here anymore. All right, does everyone see what I did here, right? I took that and brought it out here, so now it's a plus right here now. So now you're going to let the x be the negative of t in this series, and then let x be t in this series. So you have integral from 0 to x of the sum k equals 0 to infinity of negative t to the k dt plus integral from 0 to x of sum k equals 0 to infinity of t to the k dt. All right. So now, what do you do after this? Well, this is not that difficult to go ahead and write out, right? So all we need to do is go ahead and integrate this. So let's interchange the sum and the integral. So we have sum k equals 0 to infinity of, so another thing to remember is I could write this as negative 1 to the k times t to the k, and bring the negative 1 to the k outside of the integral, and then find the integral using the power rule for integral. So that will be t to the k plus 1 over k plus 1. And then I'm going to evaluate that from 0 to x plus the sum k equals 0 to infinity of the t to the k plus 1 over k plus 1, and evaluate that from 0 to x. So let me find my next page here. All right, so now that I found my page here, let's go ahead and evaluate each of these. So the first one will be sum k equals 0 to infinity of, well, that will be negative 1 to the k and x to the k plus 1 over k plus 1 minus negative 1 to the k times 0 to the k plus 1 over k plus 1, and then plus sum k equals 0 to infinity of x to the k plus 1 over k plus 1 minus, this will be, what is that going to be? Negative, yeah, so minus 0 to the k plus 1 over k plus 1. And then let's go ahead and simplify this. So it ends up being sum k equals 0 to infinity of negative 1 to the k x to k plus 1 over k plus 1, then minus a 0. Then these are both summed with the same limit. So I'm just going to combine them, all right? Plus x to the k plus 1 over k plus 1, and then minus 0. So then if I look at this, I can factor out the x to the k plus 1 over k plus 1, and I have negative 1 to the k plus 1. And then if I go ahead and I go ahead and I just, well, I write out the terms, right? I have x over 1 times 2 plus 0 plus x to 3 over 3 times 2 plus 0 plus x to the 5th over 5 times a, what is that going to be? Times a, well, a 2 again. All right, so hopefully this all is okay with all of you. And then the next term is 0. So this is actually, this isn't that difficult of a series to write out, right? It's actually 2 times x plus x to third over 3 plus x to fifth over 5, and so on. So then I hope that you can see another way to write this might actually be, well, what you want to write. You could rewrite this as k equals 0 to infinity, and since you only have every other term here, like every other power term, because every other one ended up being 0, this is actually 2 times x to the 2k plus 1 over 2k plus 1. All right. And now, why do I want to do this? Because then I can easily just find the radius of convergence for this. So as usual, let W be 2k plus 1. And so then this is a sum. W equals 1 to infinity of 2 x to the w over w. So Cn is 2 over n, and Cn plus 1 is 2 over n plus 1. So the limit as n goes to infinity of Cn plus 1 over Cn is the limit as n goes to infinity of 2 over n plus 1 all over 2 over n. So this is the limit as n goes to infinity of 2 over n plus 1 times n over 2, which ends up being 1. And so since L is equal to 1, that means R is 1 over L, which is 1 over 1, which is 1. So R is equal to 1. What a time to be alive. All right, so now it is time for our very last example of finding the derivatives and integrals of power series, or differentiation and integration of power series. So I hope that you've really enjoyed this. And here is our last example here. So here we go. We have find a function represented by the given power series and specify the radius of convergence. So again, I have to think about series that I know. And, well, another way to write this series here would be sum k equals 0 to infinity of negative 1 times x minus 1 to the k. Since both of the terms were to the k power, then this will be sum k equals 0 to infinity of, well, negative x plus 1 is the same as 1 minus x to the k power. And then if you think about what is going on here, then all I need to do is look at this known power series, which is 1 over 1 minus x. That's the sum k equals 0 to infinity of x to the k, or of something here to the k power. And here it's 1 minus x to the k power. So the 1 minus x is what's going to be to the k power, so that goes right here. So this series is 1 over 1 minus x, and that is 1 over 1 minus 1 plus x, or 1 over x. So this is a function that can be used to represent that series, or this function is represented by that series. And now let's find the radius of convergence. So I know that, well, here we go. So we know that the CK is 1. So that's all we really need to know here, right? So CK is 1, so CN is 1, and CN plus 1 is also 1. So the limit as n goes to infinity of CN plus 1 over CN is the limit as n goes to infinity of 1 over 1, which is 1. So therefore, since L is equal to 1, R is 1 over L, which is 1 over 1, which is 1. So therefore, R is 1. What a time to be alive. Unfortunately, we've come to an end here, so I'll have to bid you a fond farewell, and I hope that you really enjoyed this and you're already looking forward to the next video. Thank you and have a great day.